Hey everybody, welcome back. In the previous video, we talked about linear transformations. That's when you have some random variable and you multiply it by something and then add something to it. This comes up, for example, if you have a whole bunch of data that was originally recorded in Fahrenheit and you need to convert it into Celsius. Now that could happen a whole bunch of times. And this kind of affects a lot of our calculations, right? We have completely different units. So in this entire video series, we're going to be looking at all of these different topics, essentially looking at how a linear transformation, notice that looks like a straight line, so linear transformation, how that affects the average, that's what we did last video. Today we're going to talk about how it affects the variance. And then we're going to look at what happens when you actually have linear combinations of variables. So you transform them to different variables and then add them. So let's dive into this second video, what happens to the variance. So the idea, again, is that you've got some random variable, x, and you've got observations on x. Maybe, I don't know, 50 of them, or n of them to keep it general. Let's say that x was 80 for the first observation, 90, 70, and so forth, all the way down, who knows, to 60. And we want to create a new variable, some new variable, let's call it y or something like that takes x and multiplies it by, let's say, increasing it by 10%, and then adding 5 to it. And if we do that, then we would get 88 plus 5, which is 93. We would get 99 plus 5, which is 104. We would get 77 plus 5, which is 82. And 66 plus 5, 71. Now clearly, the average of 80, 90, 70, 60 is different than the average of 93, 104, 82, 71. So we know that the expectation of our transformed variable y is different. In fact, in the last video we saw it's equal to this. But this new set of numbers also has a different variance. So what happens there? Turns out that's also really straightforward. We can essentially ignore any additive terms. Those have no effect on the variance whatsoever. But the scale at which we measure things, that's going to affect the variance. Let's see why. Let's start out with the formula for calculating a simple variance of some untransformed random variable. We know that you're going to take each observation, calculate its difference from the mean, you want to calculate the squared differences, and then add all those up and divide by n, or n minus 1. Okay, so in other words, that is this. And I'm going to use now the expectation notation for the average rather than the x-bar. And we're squaring that. So that's the simple formula for a variance. Now we want to know, well, we've got a new variable, y. What's the variance of y? Well, we're going to have to apply that same formula. And we square that. Y is a plus bx. In this case, a is 5 and b is 1.10. But let's keep it general and say a plus bx. Let's substitute that into here. So we have a plus b for the first observation minus the expectation of y. That's the first term. We need to do that for all of our terms. So let's make this an I. And we square that. Okay, let's keep working. Rather than multiplying, rather than using the summation notation, let's just be explicit about all the stuff we're adding. So we have a plus b x1 minus the expectation of y. That's our first term. And then we have to do it for x2. All the way up until the end. A plus b xn minus the expectation of y. And let's not forget to square each of these terms. Now that's looking really hairy. And in fact, it's going to look even hairier for a moment before we're able to simplify. Notice that we have an expectation term here. So let's expand this. In the previous video, we saw this. With the expected value of y, if y is a linear transformation of some other variable, is a plus b the untransformed expectation. So let's substitute this in for each of those expectations of y. This is not going to look pretty. A plus b x1 minus this minus a plus b expectation of x. All right, that was our first term. Let's make sure we bracket that and square it. And then we need to do that for our second term. And we square it. And we do that for every one of our n terms. Now, one thing should pop out. We have a minus a. So that's good. At least we can start simplifying this thing. Let me clean my slate. Okay, so I've rewritten the formula now using a clean slate. I told you this thing would look hairy, but it's about to look a lot less hairy. Notice that we have a plus bx1 minus a, and then we just distribute that negative again and go minus b expectation of x. All of that is inside this particular squared operator. So a minus a, that cancels. And that leaves us with something that's a little less hairy. We now have no more a's, those have canceled. So we have b x1 minus, because that negative sign distributes here onto the plus sign, b the expectation of x. Now we're going to square that. And that part isn't pretty. But notice that we got rid of the a's. And that's good, because we know the punchline. The punchline is that the variance of our transformed variable y doesn't depend on a at all. So you can add anything you want to a random variable, you haven't affected its variance at all. And that's good, because we don't have any a's left over. So this applies to every single one of our n terms. Okay, now we notice that b shows up everywhere. But b shows up everywhere, but then it becomes squared. So what's that like? Well, we can pull out a b, but we got to just make sure that it gets squared. So we would have this. We would have b squared x1 minus the expectation of x squared. Okay, we can do that here. And then we would do that here. Oops, b squared x2 minus the average of x, and so forth. Maybe that step, maybe I skipped a step here. Let me switch colors for just a moment. And let's focus on this guy right here. So we've got something minus something squared. Something minus something squared. What does that equal? That's a squared minus 2ab plus b squared. Now in this case, we have something that includes a b, something that includes a b. So let's just multiply this entire thing out. Let's apply this formula to this as a and this as b. Then we would get b squared x1 squared minus 2b squared x1 expectation of x plus b squared the expectation of x squared. So we just foiled this guy right here. And notice that b squared shows up everywhere. So you can pull out the b squared, leaving you with this. And so you can see that this is a foil. That's that right there. And your b squared is this guy right there. So that's why we were able to pull out the b squared. Okay, let's keep working. Let me clear my slate. So we had left off with this equation. Just wrote it onto a blank slate. And we can keep simplifying. We have b squareds everywhere. We can pull those out. Leaving us with something much simpler. x2 minus expectation of x squared xn minus expectation of x squared. And now I want to draw your attention to this term in brackets, because now that should look familiar. Remember that the variance of x was you take each particular observation, subtract off your mean. So see how far away each observation is from the mean, square it, add all these up, and then divide by n. All right, well, that was 1 over n, x1 minus expectation of x squared plus x2 minus the expectation of x, squared. That's this. That is just the variance of x. So let's plug variance of x in for there, and that leaves us with the variance of y is something much nicer. It is b squared, the original variance of x, which is exactly what we wanted to show. So your teacher can add something to your score and multiply something by your original score that will affect the variance. And it's going to have, in fact, a squared effect on the variance. So let's just work out a quick example just to see what this means. Let's say that the original test scores were low and that the average was a 60. Your teacher was thinking about adding 5 points to everybody, scaling everybody's score up by 10%, so that the new test scores were 5 plus 1.10 times x. Now we already saw that the expected value of this is going to be 5 plus 10, the original expected value. But what about the variance of these new test scores? Well, now we know how to calculate that. the variance of y is equal to, well, we can ignore the 5, the a. So it's just going to be 1.10 squared times the original variance. Now this is a little bit, hard to interpret, squared variances. This is one reason why a lot of statisticians translate these problems into standard deviation problems. So if you were to take the square root of both sides, then you would get the standard deviation of y is equal to, so the square root of 1.1 squared, right? The square root of b squared is just b. So b. And then the square root of the variance is just the standard deviation of x. And in this form, this is much easier for us to understand. So the new standard deviation is going to be 10%, because b here was 1.10, so 10% higher than the original standard deviation. So we've increased the standard deviation by proportionately, by how much we scaled up our test scores. We can't say the same thing for variance, because the proportionality factor is squared. But for standard deviation, it works out really nicely. Let's just do another quick example. Let's say you've got some random variable, x, and its variance is 20. And you're going to create a new random variable that's a linear transformation of x. Let's say it's going to be 3, start writing, 3.14 plus 10x. What is the variance of y? Well, we know that we can ignore anything that we've added, because a doesn't show up at all over here. So the variance of y, this guy here is y. So the variance of y is just the square of what we multiplied times the original variance. Or in other words, 100 times the variance of x. So 2,000. Okay. We added stuff to it. We can ignore that. We scaled up our test scores, or whatever this x variable was, by 10. But that meant that our new variance is 100 times more. It was 10 squared more. If we were to convert this over to standard deviations by taking the square roots, then we see that the standard deviation of y is just b standard deviation of x. So 10 times the original standard deviation. So we take the square root here of 20, whatever that is. Okay, so that's just another reason why it's sometimes easier to think in terms of standard deviation, because the standard deviation reacts proportionately to how much you multiplied your original variable by. Now, at this point, you might be wondering, why do we care so much about linear transformations? Is this really important? I want to take 5 to 10 minutes to show you why this is massively important. It has everything to do with standardization. Whenever you standardize a variable, you subtract off the mean and you divide by the standard deviation. So you're adding something negative and you're dividing, but dividing is just multiplying by 1 over a number. So standardization is an application of linear transformations. And a lot of the statistics that we use in your classes, in stats classes, are z-values, are standardized values. And so you're actually dealing with the repercussions of the last two lectures all along about linear transformations.